Okay, so we know that atoms have a nucleus with electrons kind of buzzing all around it. But you know what? It's not a chaotic free-for-all. There's actually a very specific, super orderly system for how they're arranged, almost like a secret code. And today, we are going to crack that code. Let's get into it.
So how do they do it? Do they just kind of float around and pick a spot they like? No way. There is a strict rule book they all have to follow, kind of like assigning seats in a massive, massive stadium. And by the end of this, you're going to be the expert who knows that rule book inside and out.
But before we can even start to open that rule book, we need to understand one final, absolutely crucial piece of the puzzle about the electron itself. We've talked about its energy, the shape of its orbitals, but there's one more property we've been missing.
So scientists started noticing something a little strange. You know those yellow street lamps? Well, when they looked really, really closely at that yellow light, they saw it wasn't one single line of yellow, it was actually two lines, packed incredibly close together. This tiny detail, they called it the sodium doublet, was a huge clue that our picture of the electron just wasn't complete. The quantum numbers they had just couldn't explain it.
To solve this mystery, they introduced a fourth quantum number, the spin quantum number, or what we call m sub s. The best way to think of it is that an electron has its own internal spin. It's a fundamental property, just like its charge or its mass. Now, it's not literally spinning like a toy top, but it behaves as if it has its own tiny magnetic field.
And here's the cool part. This spin can only have two possible orientations. That's it. We call them spin up and spin down. For spin up, the value is +1/2, and we draw it as an upward arrow. For spin down, its value is -1/2, and we draw it as a downward arrow. Just two choices. Simple.
Okay, now that we have all four quantum numbers, we've got the complete toolkit. We finally have all the information we need to start writing down the complete address for every single electron in an atom. And this formal address, it has a specific name.
It's called the electronic configuration. Now, this is a key definition you'll want to lock in for your exams. It's simply the way electrons are distributed among the shells, subshells, and orbitals. Think of it as the master blueprint for the atom's entire electron layout.
So, we write it in a standard notation that you see here, n, L to the power of x. Let's break it down. N is the main energy level, L is the subshell, remember S, P, D, and F, and that x is just how many electrons are in that subshell. So for our simplest example, hydrogen, with just one electron, it goes into the lowest energy spot available, the first shell, the S subshell. So its address is just 1s1. Easy enough, right?
But what about something like helium, which has 2 electrons, or carbon with 6? We can't just stick them anywhere we want. This is where that rule book I was talking about comes into play. There are 3 fundamental principles we have to follow, and trust me, the order really matters.
All right, let's kick things off with rule number 1. This is the most fundamental rule of them all. It sets a hard, non-negotiable limit on how many electrons can share the same space, the same orbital.
This is the famous Pauli exclusion principle, and it states that every single electron in an atom must have a unique set of 4 quantum numbers. It's like a personal ID number for each electron. No two can be exactly the same. They might share the first 3 numbers, but that fourth one, the spin, has to be different.
Now let's see how this plays out with helium. It's the perfect example. As you can see in the table, its 2 electrons are both in the 1s orbital. So their n, l, and ml values are all identical. To obey Pauli's principle, their fourth quantum number, their spin, must be different. One has to be spin up +1/2, and the other has to be spin down -1/2.
And this leads to a brilliant and super simple consequence. Since there are only 2 possible spin values, an orbital can hold a maximum of 2 electrons. That's it. Full stop. And if it does hold 2, they have to have opposite spins, which means their little magnetic fields cancel each other out. This is a non-negotiable law of the atomic world.
Okay, so we know we can put up to 2 electrons in any given orbital. But which orbital do we fill first? The 1s, the 3d, the 4p? There's an order to it, and that's where our second rule comes in. It's called the Aufbau Principle. Aufbau is a German word that means building up, and that's exactly what we do. We build the atom up, 1 electron at a time, by always placing them in the lowest energy orbitals available first. Why? Because nature is efficient. It always prefers the most stable, lowest energy setup.
So how do we know the exact energy order? Well, there's a simple little trick for it, called the n plus L rule. You just add the n and L values for an orbital. The lower that number, the lower its energy.
And what if two orbitals have the same sum? No problem. In that case, the one with the lower n value gets filled first. It's really as simple as that.
Following that n plus L rule gives us this exact sequence right here. 1s, then 2s, 2p, 3s, 3p, and then, now pay attention, here's the tricky part that trips a lot of people up, 4s gets filled before 3d. Why? Let's check our rule. For 4s, n is 4 and L is 0, so the sum is 4. For 3d, n is 3 and L is 2, so the sum is 5. Since 4 is less than 5, 4s has lower energy. The rulebook is crystal clear. This is the order you've got to memorize.
All right, we've got our capacity rule, we've got our filling order rule. Let's move on to the final rule. This one tells us how to handle orbitals that have the exact same energy, like the 3 different p orbitals on a subshell. We have a special name for these, degenerate orbitals.
This is Hund's rule. It basically says that for orbitals of the same energy, electrons will spread out and take their own orbital first before they ever start pairing up. The easiest way to think about it is like people getting on an empty bus. They each take their own empty row of seats before anyone sits next to someone else. It all comes down to energy. Electrons repel each other, so keeping them apart is just more stable.
Let's see this in action with carbon. Its configuration is 1s squared, 2s squared, 2p squared. The first 4 electrons fill up the 1s and 2s orbitals, no problem. The last 2 have to go into the 2p subshell. Now, according to Hund's rule, they don't pair up in the first p orbital. Nope. Instead, one goes into the first p orbital, and the second one goes into the next empty p orbital. And notice, they both have the same spin. This is the lowest energy, most stable arrangement possible.
All right, that's the complete rulebook, Pauli, Aufbau, and Hund. Let's do a quick summary, and I'll give you some key tips that are absolutely crucial to remember for your exams.
A super common point of confusion is the difference between Pauli's and Hund's rules. So here's the key. Think of Pauli's principle as the capacity limit for a single room. That's an orbital. Maximum 2 occupants. Hund's rule is the seating arrangement for a suite of identical rooms. That's a subshell. Everyone gets their own room before anyone has to share.
Okay, here is your rapid revision checklist for exams. Remember the quick formulas for max electrons in shells and subshells. And this is the most important part. Always apply the rules in order. First, use Aufbau to find the right energy level. Then, place your electrons respecting Pauli's 2 per orbital limit. And finally, use Hund's rule for the seating arrangement. Get that order right, and you will avoid the most common mistakes every time.
So, what's the big takeaway from all this? The arrangement of electrons might seem really complex at first, but it is absolutely not random. It's governed by a beautiful, logical set of rules. If you can master these 3 principles, Aufbau, Pauli, and Hund, then you've mastered the language that explains the structure and behavior of every single atom in the entire universe.